Have you ever sat on a plane, looked out the window at that absolutely massive engine hanging off the wing, and just wondered, how can something so powerful be so, well, quiet? I mean, compared to the jets of the past. Today, we're going to pull back the curtain on the brilliant engineering that makes modern air travel possible, the turbofan engine.
Right, so let's start with that question. If you've ever watched old movies or newsreels from the 50s or 60s, you know that sound, that high-pitched, deafening scream of early jets. Airports used to be unbelievably loud places. Today, it's a whole different ballgame. I mean, they're not silent, but the sound is this deep, powerful whoosh, not a scream. So what happened? What changed? Well, the answer is a complete revolution in how we think about building a jet engine.
You know, to really get why the new way is so good, we first have to understand the old way and its problems. The very first jetliners were powered by what are called turbojets, and look, they were an absolute game changer. They let planes fly faster and higher than ever before. But, and this is a big but, they had two massive problems. They were incredibly thirsty for fuel, and they were deafeningly, painfully loud.
Yeah, so that's the bottom line. Extreme fuel consumption and a whole lot of noise. See, a turbojet works by sucking in a pretty small amount of air, squeezing it, setting it on fire, and then just blasting that super hot gas out the back at insane supersonic speeds. Now that creates a ton of thrust, no doubt. But for a passenger plane that's just cruising along below the speed of sound, it's a terribly inefficient and noisy way to get the job done.
But then, someone had this truly elegant idea. I mean, it's one of those beautiful moments in engineering where one innovation solves two huge problems at the exact same time. And that idea was the bypass engine, which we all now know as the turbofan. So the big aha moment was this realization. What if we use the hot, powerful core of a turbojet, not just to push the plane forward, but to be a power source, a gas generator, that does one main job, spinning a gigantic fan at the front? This was huge because it meant you could separate the part that makes the heat from the part that makes most of the push. It just gave engineers a whole new playbook to work from.
And this gets to the absolute heart of the idea, the core physics principle of it all. It is way more efficient to move a large amount of air slowly than it is to move a small amount of air really, really fast. Think about it like a helicopter. You could try to lift it with a tiny, super fast rotor powered by a massive engine, but you'd burn a ton of fuel. Or you could use a much bigger, slower moving rotor, which is way more efficient. The turbofan is basically applying that same exact logic to a jet engine.
Okay, so how does this actually work in practice? Well, it all comes down to a really clever design that takes the air coming into the engine and splits it into two completely different paths. It's a tale of two air streams. So as you can see here, a tiny little bit of that incoming air gets sent down the middle into the hot core. That's the orange path. In there, it's business as usual. It gets compressed, mixed with fuel, and boom, ignited, just like in an old turbojet. But, and this is the key, the vast majority of the air, like most of it, completely bypasses the hot core and just flows through that cool blue channel around the outside, pushed by that big front fan.
And what's really happening inside is basically an engine within an engine. You've got these two main rotating shafts, or spools, that spin totally independently. That long, low-pressure spool, marked A, is what connects the turbines way back in the hot exhaust to that huge fan at the very front. Then there's a separate, shorter, high-pressure spool marked B that just runs the compressor for the core. This design is genius because it lets each part spin at its own perfect speed for maximum efficiency.
Okay, this brings us to probably the single most important term you need to know to understand any turbofan engine. It's the bypass ratio, or BPR. All it is a simple ratio. It tells you how much air goes around the hot core compared to how much air goes through it. That's it.
So what does a high bypass ratio actually mean in the real world? Well, a modern engine on something like a 787 or an A350 might have a bypass ratio of, say, 10:1. Now think about that. That means for every 1 pound of air that goes through the fiery hot core, 10 pounds of cool air are getting pushed past the outside by that fan. And it's that huge mass of bypassed air that's generating most of the engine's thrust.
Now, what's so cool about this bypass idea is that you can tune it for completely different jobs. You can design a high bypass engine, which is perfect for an airliner, or a low bypass engine, which is what you'd want on a fighter jet. It's the same core principle, just optimized for totally different goals.
So let's break this down because the comparison tells the whole story. On one hand, you have high bypass turbofans. They're for commercial airliners. They are all about sipping fuel and being quiet, and almost all of their thrust comes from that giant fan at the front.
On the other hand, you have low-bypass turbofans for fighter jets. Here, it's all about raw speed and power. Most of the thrust comes from the hot core jet, and they're specifically designed to be cranked up to 11 with an afterburner.
And you can literally see the difference in their philosophy just by looking at them. The high bypass engine on the left is dominated by that enormous front fan. The fan is the engine, practically. Now look at the low bypass engine on the right. The fan is way smaller in proportion, because in that engine, it's the powerful, hot core that's the real star of the show.
And that powerful core on military jets, it allows for something truly spectacular, the afterburner. What's an afterburner? Well, it's basically a second stage of combustion, where they just dump raw fuel directly into the super hot exhaust. The result is that incredible blue flame you see, and a massive, but very temporary, boost in thrust. It's what they use for takeoffs, intense combat maneuvers, or punching through the sound barrier.
All right, so let's bring this all back home. How did this fundamental shift in engine design really change air travel for all of us? Well, the impact was absolutely huge. Flying became way more efficient, a whole lot quieter, and honestly better for the environment.
This graph here really tells the story perfectly. Propulsive efficiency is just a fancy way of saying how good an engine is at turning fuel into forward push. And if you look at the blue line for the turbofan, you see it peaks. It hits its sweet spot right around 500 to 600 miles per hour. That's the exact speed an airliner loves to cruise at. It's simply the perfect engine for the job, leaving the old turbojets, that red line, completely in the dust at those speeds.
And what about the noise? Why are they so much quieter? Well, it comes right back to that core idea. Instead of a narrow, super-fast jet of hot gas that's violently ripping and shearing against the calm air around it, which creates a ton of noise, you now have this huge, wide column of much slower-moving air. The mixing is just gentler, less turbulent, and as a result, a whole lot quieter. And engineers have gotten even more clever about reducing noise. Seriously, next time you're at an airport, walk over to the window and look at the back of a modern engine. You'll probably see these sawtooth patterns called chevrons. This is just a brilliant piece of acoustic engineering. Their only job is to help the hot air from the core and the cool air from the bypass duct mix together even more smoothly and quietly. Super smart.
So, the high bypass turbofan has been the undisputed king of commercial aviation for over half a century. But you know engineers, they never stop pushing. The quest for even better efficiency is never, ever over. So, what's on the horizon?
Well, they're pushing the limits in every direction you can imagine. People are working on engines with even higher bypass ratios, like 15-to-1 or more. They're using incredible new lightweight materials, like ceramic composites that can handle more heat. There are geared turbofans, which add a gearbox between the fan and the spool, letting each part spin at its absolute perfect speed. And then you have some really wild ideas, like these counter-rotating open rotors that look more like something out of a sci-fi movie.
So we've seen this incredible journey, right? From the screaming, inefficient turbojets of the early jet age to the quiet, unbelievably efficient, high-bypass turbofans that connect our world today. But this story is definitely not over. Is the next giant leap going to be a radical new design like an open rotor, or something completely different like hybrid electric flight? We don't know for sure, but one thing is certain. The quest to build the perfect engine is far from over.